When you look at a piece of graphite, you are looking at a macroscopic illusion. The bulk material we use in pencils or industrial lubricants is actually a stacked deck of highly structured, separate atomic grids. If you peel away all the surrounding bulk and isolate just one of those layers, you are left with graphene, a true two-dimensional crystalline allotrope of carbon. Material science has spent decades analyzing this structure, yet its elemental composition remains carbon atoms locked into a hexagonal honeycomb lattice. This exact two-dimensional geometry acts as the universal building block for nearly every other structural form of carbon. Stack the layers, you get graphite. Wrap into a sphere, forming fullerenes. Roll into a cylinder, carbon nanotubes. A sheet strictly confined to a single atomic layer consistently outperforms massive three-dimensional structures across mechanical, electrical, and thermal testing. To understand how a material one atom thick can achieve this, we have to construct it from first principles. We will build the 2D lattice mathematically, starting from a single carbon atom. We need to trace the exact line from subatomic electron configurations to macro-level engineering metrics. Graphene's record-breaking physical properties are a strict mathematical and physical consequence of its two-dimensional atomic geometry. On screen is a top-down view of our starting point, a single carbon atom. To begin building the lattice, 3 of carbon's valence electrons stretch outward, locking into neighboring atoms at exact 120-degree angles. This specific, flat geometry is called sp² hybridization. When you propagate this pattern outward, you create the continuous hexagonal mesh of the graphene sheet. If we isolate a single connection between 2 carbon atoms, we see what holds the mesh together. These are sigma bonds. They are incredibly dense, locking the atomic nuclei at a distance of approximately 0.142 nanometers. Because the bond length is so short, the nuclei are held tightly together. This translates directly to immense rigidity across the planar framework. When physical stress is applied to the edges of the sheet, the load distributes across this unbroken, tightly knit mesh without failing. Pulling back to observe the macroscopic metrics of the structure, the data reveals an intrinsic tensile strength of 130 gigapascals. We pair that with a Young's modulus, which measures a material's physical stiffness or resistance to elastic deformation, of 1 terapascal. Structural steel yields under a fraction of that load. To achieve the same resistance to deformation using steel, you would need a barrier vastly thicker than graphene's single-atom profile. The sp² hybridized geometry mathematically necessitates a layer measuring exactly 1 atom thick operates with more than 100 times the strongest equivalent steel. If we rotate our 2D lattice 90 degrees to an edge on view, we can address the mechanical rigidity we just built. Carbon has 4 valence electrons, and we have only used 3. That 4th electron occupies a pz orbital. Unlike the flat sigma bonds, these orbitals are oriented strictly perpendicular to the carbon plane. Because the carbon atoms are packed so closely, these perpendicular orbitals overlap. They hybridize collectively, forming continuous, delocalized fields known as the pi and pi star bands. In a single 2D layer, these energy bands meet at discrete points, where the relationship between an electron's energy and momentum becomes linear. This unique intersection allows graphene to function as a zero-gap semiconductor. Because of this linear intersection, electrons travel through the plane as direct fermions, massless particles that are not subjected to the effective mass that slows down charge carriers in traditional 3D materials. These particles move through the lattice at roughly 1 million meters per second, a measurable fraction of light speed. In macroscopic terms, this translates to a carrier mobility exceeding 200,000 square centimeters per volt second. At room temperature, electricity flows through graphene with significantly less resistance than it does through copper. The same continuous band structure provides a pathway for heat dissipation. Phonons travel so incredibly efficiently through the lattice that graphene's thermal conductivity surpasses both diamond and bulk graphite. Optically, the thinness of the atomic sheet means it interacts minimally with photons. The material absorbs only 2.3% of white light, giving it a transmittance rate of 97.7%. The same perpendicular pi band architecture that provides extreme structural strength also enables conductivity beyond copper and near total optical transparency. This matrix charts the primary engineering bottleneck for the entire industry. The pristine metrics we just calculated require mathematically flawless crystals. As we plot quality on the y-axis against production scalability on the x-axis, a strict compromise emerges. In the top left, we have mechanical exfoliation. This is the original sticky tape method, where layers are physically peeled away from bulk graphite. The resulting crystals are structurally flawless, but peeling tape by hand generates microscopic yields. The lack of scalability renders it commercially useless for mass production. Moving across the x-axis requires a trade-off. Achieving industrial volume strictly requires sacrificing some degree of atomic perfection. Chemical vapor deposition, or CVD, sits in the upper right. This process grows graphene by reacting hydrocarbon gases over transition metal substrates like copper at high temperatures. CVD maintains high lattice integrity across larger surface areas, making it the optimum compromise when continuous electron flow is mandatory. Liquid phase exfoliation uses intense ultrasound to separate graphite within a solvent. Finally, the reduction of graphene oxide, or RGO, achieves massive scalability by chemically treating and then reducing bulk graphite. The chemical baths introduce oxygen atoms that permanently scar the carbon lattice. These structural defects cause a drastic drop in both tensile and electrical performance compared to a flawless sheet. Looking at this commercial matrix, successful engineering requires matching the correct level of material defect to the precise application. For example, advanced composites, epoxy resins, and 3D printing filaments do not require perfect electron mobility to function. They rely entirely on the sigma bonds. Dispersing highly scalable, chemically defective RGO flakes into a polymer matrix leverages the raw tensile strength of the lattice, reinforcing the host structure. High-frequency transistors and flexible optoelectronics have a strict zero-defect requirement. To function, these devices require the uninterrupted charge carrier mobility provided by the continuous pi band. Therefore, they rely exclusively on high-quality CVD manufacturing. Energy storage engineering, particularly the development of lithium-ion batteries and supercapacitors, utilizes a different physical variable entirely. Liquid phase exfoliated flakes maximize the exposed geometry of the 2D plane, providing a massive surface area to volume ratio. This physical density accommodates significantly more ions, decreasing charging times while increasing energy capacity. In thermal management, engineers incorporate graphene into heat sinks and thermal interface materials, particularly inside high-density electric vehicle battery packs. Even in fragmented forms, the 120-degree atomic geometry efficiently channels heat away from localized hotspots, preventing catastrophic thermal runaway. The transition from lab to industry now depends on manufacturing processes that can scale this two-dimensional architecture without losing the properties that make it unique.